Welcome to this video on section 3 on Cramer's rule. The goal of this section is to use determinants to solve linear systems in a very special case. So although for the moment we only know how to calculate the determinant of n by n matrices with n less than or equal to 3, the following theorem does apply for any n. So theorem 6.3.1, Cramer's rule. Let A be an n by n matrix where determinant of A is non-zero. Then the linear system of n equations in n unknowns, so a square system, represented by the matrix equation AX equals B, so A is the coefficient matrix, may be solved by xi, so xi is the ith variable of the system. Xi can be calculated as the determinant of A sub I divided by the determinant of A. Now I haven't told you what A sub I is, but just note that this is true for all the variables in the system, so for I equals 1 to n. So this A sub I, it is a new matrix. It's a matrix created from matrix A, from the coefficient matrix, by replacing the entries in the ith column, so the column that corresponds to the variable that we're solving for, x sub I, replacing the entries in that column with the entries of B, the constants. So that may not be obvious how that will look, but let's go and do example 6.3.1 to get an idea of what that actually looks like in practice. So in this example, we're asked to consider the linear system given here. We're asked to verify that Cramer's rule applies and then use it to solve the system. And then finally, as a last step, we're going to check our answer. So this linear system is a square system. We've got 3 equations. We've got 3 unknowns. And so our coefficient matrix, we're going to let A be the coefficient matrix. It is, in fact, a 3 by 3. So our system is square, and that is the first thing that we need for Cramer's rule. We need an n by n matrix, and we've got one. We have a 3 by 3 matrix. Now that's not enough. We also need the determinant to be non-zero. So let's calculate the determinant of A. So that's the determinant of our coefficient matrix. So we've got 1, 2, 1, 1 minus 1 minus 1, minus 9, minus 1, 3. And of course, as always, we recopy the first 2 columns. And we're going to do our triple diagonal product. So we're going to get here minus 3, and then minus 1, and I forgot a minus sign here, plus 18, minus, and then up here, minus, minus, so those cancel out. We get 9, plus 1, plus 6. And so we have minus 4 plus 18, that is 14, minus 16, which is minus 2, and in particular, that is not 0. So we have the determinant is not 0 of a square system, and so we have, therefore, that Cramer's rule applies. So how does it apply? What do we do to solve? Well, we're going to go in order. So if we solve for x, we need to create this variable a sub I. It's the first variable, so we're going to call that a sub 1. When I only have 3 variables, I like to name it in terms of the variable, so you might name that a sub x as well. And Cramer's rule tells us that what we do is we take the column of x, so the first column here, and we replace it by the constants. So I'm going to take that 2, 0, 1, and I'm going to put that in the column of x because I'm solving for x. And the rest of the columns remain the same. So I'm going to calculate this determinant because that's what I need as my numerator here. So I'll calculate this determinant again by recopying. And what do we get here? Minus 6 plus 1 plus 0 minus 3 minuses, so minus 9 plus 2 plus 0. So we have minus 5, and then here minus 7, so 7 minus 5 is 2. Now, that is the numerator of the x fraction, and the x fraction has this 2 in the numerator and the determinant. Well, I should maybe rewrite that. So we have the x, according to Cramer's rules, the determinant of a sub x over the determinant of a. Determinant of a sub x we just calculated as 2. Determinant of a was what we calculated before. That's minus 2 minus 2 over 2 gives us an x value of minus 1. So that is just the x of the solution. We need to repeat this process for the y and the z. Now we're going to do this in a very similar way, but I'm going to replace the constants into each of the columns of y and then the constants in the column of z in turn, right? We just replace it into x because we were solving for x. Now if we want to solve for y, we're going to need a second matrix. Cramer's rule would call that a sub 2. I'm going to call it a sub y because I'm solving for y. And so this time it is the y column that gets replaced by the constants because I'm solving for y. So the first column remains the same as in A, 1, 2, 1. And then in goes b for the y column, and the z column remains the same. And once you understand that, you understand Cramer's rule. So it's just a matter then of calculating the remaining determinants. So we're going to get here 0 minus 2 plus 18 minus 0 plus 1 plus 12, which is, so 16 minus 13 is 3. Now that's just the determinant of a sub y, so if we want y, Cramer's rule tells us we're taking the determinant of a sub y over the determinant of a. So that means we have 3 over minus 2 again was the determinant that we got for a, and then that just gives us minus 3 halves. One last variable left to do then, that's a to solve for z, so we need the matrix A3 or A sub z, and we replace now the z column by the constants. So the first two columns remain unchanged in the coefficients, right? These are the coefficient of the x and the y, and then the z column is going to be replaced by the 2, 0, and 1. So 2, 0, minus 1. 1, 2, 1, 1, minus 1, 1, and what do we have here? So we've got positive 1, 0, positive 4, minus, and here minus 2, plus 0, and this is, what is it now? Minus 2. And, oh, what happened here? I lost a minus again. I'm always losing minuses. That changes, so what does that change? That changes this to a minus 4. So I end up by having 1, so that's minus 3, minus 4, 4 minus 3 is 1. Lastly, then, we need z is determinant of a sub z over determinant of a, which is going to be this 1 over the original determinant, minus 2, or minus 1/2. And so we have solved using Cramer's rule to get the solution of the system as x is minus 1, y is minus 3/2, and z is minus 1/2, a unique solution to this linear system. We were asked to check our answer, right? We were asked to check the answer from Cramer's rule, that this wacky process actually does yield the solution to the system. And so to check, of course, we need to plug all of these into the original equations and make sure that they work. So the first equation, x plus y minus 9z, I'm hoping that this will give me 2. So if we plug this in, we have minus 1 minus 3/2. Minus minus is plus 9 times 1/2, 9/2. This is minus 2 over 2 minus 3 over 2, so minus 5 over 2. Plus 9 over 2 is minus 9 minus 5 plus 4, 4 over 2, which is 2, which is exactly what we were supposed to get. So at least the first equation is satisfied. Now for a linear system, you remember you've got to satisfy all the equations, so we have to check all of them. So 2x minus y minus z, we're hoping to get 0 here, so 2 times minus 1 Minus minus is plus 3 halves, and minus minus again is plus 1 half. So I've got minus 2 plus 4 over 2. That's minus 2 plus 2, which is 0. Again, that is exactly what we were supposed to get for the second equation. So we are looking good. We have one equation left to do, and that is x minus y plus 3z. This should give us minus 1. So minus 1 minus minus is going to be plus 3 halves minus 3 times 1 half. So minus 3 halves minus 1 plus 0. There is our minus 1. And we indeed do have the solution here given to us by this strange rule, Cramer's rule, where you're taking the ratio of determinants for each variable to solve the system. In the next video, we'll take a look at this little takeaway and have the big picture of our methods for solving linear systems when we have a unique solution.